Hi, it's Iman, and today I'm going to share a simple and quick way to check the seismic vulnerability of buildings. Using just a calculator and some basic building data, you can determine whether a building is at risk of collapse or will likely survive a major earthquake. So let's get to it. Alright, this approach was first introduced in 1997 by Hassan and Sozin for low-rise buildings up to 4 stories. And then in 2024, it was expanded to include low-rise and mid-rise buildings, covering buildings from 2 to 16 stories, using data from 15 ground motions across 12 different countries. Okay, let me first explain the general idea behind this method. The method basically focuses on two key parameters, the wall index and the column index. Once you have them, you can determine their intersection and find the corresponding point on the plot. And each point here represents a building, and the damage it sustained is categorized into 4 levels. Buildings in this category actually experience no or negligible damage during the earthquake. Light, this category represents minor damage, so the building remains functional. Moderate, here we see significant damage that would require repairs before the building can be fully functional again. Finally, buildings in the severe category suffer extensive damage or are likely to collapse, posing a serious safety risk. Okay, now I'm going to calculate these two indices for a building whose data is provided in the paper. And I've prepared a spreadsheet where I'll explain everything step by step. Okay, this is the ground floor plan of a 3-story elementary school. All units are in meters. The plan dimensions are 36 by 18 meters. And then the RC walls are highlighted in green and the masonry walls in yellow. The total length of RC walls in the Y direction is the sum of all green lines in that direction, which is 45 meters. Similarly, in the X direction, the total length of RC walls is 14.8 meters. Okay, and then the thickness of the RC walls is 30 centimeters. So the total cross-sectional area of RC walls is easily calculated by multiplying the length by the thickness. Similarly, for masonry walls, we calculate the total cross-sectional area in each direction, X and Y. Length times thickness. All right. So far, these are the building's basic details. Now let's see how we can assess its damage risk against a major earthquake. Okay. So, as you can see, the wall index is calculated as the ratio of A sub WT to A sub FT, where AWT is the sum of the cross-sectional area of RC walls plus 1/10 of the cross-sectional area of masonry walls. And I have calculated it in this cell. Okay. AFT actually is the total floor area of the entire building, which is calculated here by multiplying the plan dimensions by the number of floors. Okay. Now, I can calculate the wall index for both the Y and X directions. And finally, the minimum value between the two is taken as the wall index for the building, which is 0.3%. Okay. Next, to calculate the column index, we need the parameters ACE and AFT. And remember, we already have AFT calculated earlier. According to the definition, ACE is half the total cross-sectional area of the ground floor columns. So, there are 17 columns shown in red, each with dimensions of 30 by 70 centimeters, giving a total cross-sectional area of 3.57 square meters. And we call it A sub col. Okay, half of this value becomes A sub CE, and I've calculated in this cell. All right. So we have ACE and AFT. So the column index is then easily obtained by dividing ACE by AFT, which gives 0.09%. So to summarize, the wall index is 0.3% and the column index is 0.09%. And their intersection on the plot is this hollow square, indicating that the damage state is classified as moderate. Okay, great. And also, our calculations perfectly matched the results excuse me, mentioned in the Sozens paper. All right. As I mentioned earlier, this method has recently been extended to include a larger data set of buildings. If we look at figure 11 in the paper, it provides us with a very practical plot. What's interesting is that these 1,600 buildings were designed and constructed according to the building codes of 12 different countries. Despite the huge diversity in the buildings, codes, and soil types, this plot clearly shows that if the wall index is less than 0.2% and the column index is less than 0.5%, the building is highly likely to experience severe damage or collapse. And one final note, if the system is a moment frame, obviously the wall index is 0. So to prevent collapse in such cases, the column index must be greater than 0.5%. However, meeting this requirement may not always be feasible because of architectural or economic constraints. Actually, the valuable insight here is that these results are not just theoretical. They are based on real buildings that have faced real earthquakes. Whether the buildings were well designed or poorly built, their performance in strong earthquakes provides a true seismic laboratory for understanding structural behavior. Okay, thank you so much for watching. And if you enjoyed this video, please like and subscribe for more. Be well.